In parts A and B, the question is asking us to find the units of constant C and constant B. In order to understand that, let's take a look at the equation that gives the position of the particle moving along the x-axis. Now, the first term in the equation is x, it's the position, and of course position is measured in meters. And what that means is that this quantity right here, as well as the other quantity here, must also be measured in meters. That way, we would have meters on the left side and meters on the right side. It would be dimensionally consistent. So what we'll do is we'll take the CT squared, and we're going to just set that equal to meters. And we're going to solve that for the constant c. And of course, to do that, we would divide both sides of the equation by t squared. This cancels it out on the left-hand side. And we can see that c would equal meters divided by time squared. Now, of course, time is measured in seconds. So if we substitute the dimension of seconds for t, we would have meters per second squared. This would be the correct unit for the value of c. We're going to do a similar exercise for the other term, bt cubed. So once again, we have set that term equal to meters. We're going to solve this for b by dividing both sides by t cubed. And we learn that b is equivalent to meters divided by time cubed. We'll substitute seconds in for time again, and we can see that b would have the dimension of meters per second cubed. So this would be the correct answer for the part B of this question. Now in part C, we are asked the following question. It says, what time does the particle reach its maximum positive x position? So let's take another look at the position equation. Here's our position equation, and the question also noted that the numerical values of c and b respectively will be 3 and 2, so let's plug those in. Now from calculus, we've learned that if we're trying to find the maximum value of x as a function of time, that we would have to compute the derivative of that function. So what we'll do is calculate x prime, which is the derivative of our position function. We're just going to use some basic power rules. We're going to multiply 2 by the coefficient 3. That's going to give us 6 times t, and then we subtract 1 from that original power, so it's t to the 1. And then minus, same power rule here, 3 times 2 is 6 times t, and then we subtract 1 from the power. This gives us 6t squared. We're going to set this equal to 0 because we seek the maximum value. And to solve this, we could factor out a 6t. The remaining factor would be 1 minus t. This is still equal to 0, and then to solve for the two time values, we will set each factor equal to 0. In the first case, if we divide both sides of this by 6, we will see that t is equal to 0. In the second case, if we subtract 1 and then divide by -1, we have t is equal to 1. Now, we have to figure out at which time we would have a maximum positive x position. So what we'll do is plug these time values back into our position equation. So for example, if we calculated x at a time of 0, we would have 3 times 0 squared minus 2 times 0 cubed. If you work this out, you get 0 meters for the position. Let's plug in 1 second next. And when you simplify that, you get 1 meter. So these are the possible maximum position values. But remember, the question wanted the maximum positive position. You go back and check it out right here. At the very top, it says, what time does the particle reach its maximum positive x position? So we're looking for the positive x position. That would be the second case, the 1 meter. That's positive position right there. So the correct answer for this part of the question will be at a time of 1 second. That is when the particle reaches its maximum positive position. So that's the answer for part C. Let's take a look at part D. And it says, from 0 to 4 seconds, what distance does the particle move? And perhaps to understand this, we can draw a sort of position graph to monitor where the object is located at different times. So for example, we start at time 0. And at time 0, we remember we had plugged 0 into the position function and we had gotten 0 meters. So the particle basically starts at 0 meters right here. But then we learned at time 1 second, and we had plugged in 1 second into the position function, we had gotten a position of 1 meter. So now the particle would be located right here. But we're going all the way up to 4 seconds, so let's plug 4 into our position equation. And this outcome is interesting because you're going to get a position equal to negative 80 meters. So that means that after 4 seconds, the particle would be located along the negative x-axis. Now, this drawing won't be to scale, of course, but we can imagine that negative 80 meters would lie somewhere to the left of x is equal to 0 meters. So it would be located over here, and this is after 4 seconds. So now we just want to sort of monitor the particle as it traverses these positions across these times. So for example, you start again at 0 meters. After 1 second, the particle has traveled 1 meter. We could write that down just again to keep track. But then notice after 4 seconds, it has to sort of turn around and go all the way back to a position of negative 80. So what the particle would have to do is it would have to turn around, travel back to the origin, so that's another 1 meter of distance, and then it would have to continue moving to the left until it reached a position of negative 80 meters. So that would be an additional 80 meters of distance traveled. So you can see that the total distance would just be the sum of those individual distances. That would give us 82 meters for that total distance. So this would be the correct answer to part D. Let's take a look at part E, which asks, what is the particle's displacement? Now, this is a little easier to calculate than distance because displacement, which is symbolized by delta x, is equal to the final position minus the initial position. Now, we're going from 0 to 4 seconds. So the final time would be the position after 4 seconds, and then the initial time would be, or the initial position, would be the position at 0 seconds. Now remember, we've calculated those positions. We plugged 4 seconds into the position function and we got negative 80 meters. We plugged 0 seconds into the position function and got 0 meters. So we can see that the displacement delta x would simply equal negative 80 meters. So this is the correct answer to part E. Now, in the next several parts, we're going to calculate the velocity at various time values as well as the acceleration. So to get the velocity, what we do is return to our position function, and then we calculate its derivative, just like we did earlier. And this time, instead of calling the derivative x prime, we will equivalently call it v for velocity. So in other words, the derivative of your position function will give you the velocity. So we just do our power rules again, just like earlier. This is 6t minus 6t squared, and then what we'll do is just plug in these time values, 1, 2, 3, and 4 seconds. So let's just go ahead and plug them all in right now. So we've plugged 1, 2, 3, 4 seconds in for the velocity function, and we obtain the following results. For part F, you should get 0 meters per second. For part G, it's negative 12 meters per second. Part H was negative 36 meters per second, and then part I was negative 72 meters per second. So those would be the correct answers for those parts of the questions. Next, we're going to compute the acceleration, and it's very similar. This time, we're going to start out with the velocity function rather than the position function, and we're going to compute its derivative. And the derivative of velocity is acceleration. So you could write this as v prime, but for the purposes of these parts of the question, we will call that acceleration. Again, we're doing a derivative. The derivative of 6t is just 6, and then we have another power rule here. 2 times 6 is 12 times t to the power of 1. Let's go ahead and plug in the exact same times that we had for the velocities. And then we just simplify. So for part J, you should get negative 6. This is acceleration, so this is meters per second squared. Then for part K, when you plug in 2 seconds, you should get negative 18 meters per second squared. Plugging in 3 seconds for part L, you'll get negative 30 meters per second squared. And then the final part, plugging in 4 seconds, you will get negative 42 meters per second squared. So these are the accelerations at times 1, 2, 3, 4 seconds.